All right. Good evening, everybody.
Good evening.
A few of the stalwarts are not here. Tim is, I don't know where he is. He's interstate. It could be anywhere. And our treasurer's wife has got COVID now. He had COVID. Richard had COVID, and now Sue's got it. Okay, so I'd like to introduce you tonight to John Cummins. So John is the brother of a very old friend of ours from Queensland, who we met when we first arrived in this country, and the kids were very young, and we still keep in contact. So, and Kathy's responsible for dobbing you in for this gig.
She's responsible for lots of things in my life.
Okay.
Ever since I was little.
Right. So, so John is a software and computer science geek, I think.
Yeah.
So John has been through 2 successful tech startups, and has also worked in senior leadership roles at corporations such as NTT, Symantec, British Telecom and Telstra, and he has built and managed global software teams, and is passionate about software engineering and still codes.
Yes.
That's excellent. And, this is the most important thing, outside work, he's doing a ground-up restoration of a 1962 MGA Roadster. Plays golf and is a keen Formula One fan. And on top of that, John also does very interesting tech work and does a lot of travelling.
I do, but
Yes.
I'm slowing down on the travelling now as I get older.
So John, we really appreciate you coming to the club tonight. A few people are really interested in your talk, for various reasons can't be here, and hence the videoing,
Okay.
if that's okay with you.
Not a problem at all.
Thank you. So over to you, John.
Thank you. Good evening, everybody. I brought a bit of shopping with me just to help the discussion. But when we talk about laser comms, we talk about a laser terminal, and I thought it would be good to bring a laser terminal along and actually show you what one looks like. So that's not from Woolies, but you can pass that one around. Normally they're very delicate precision instruments. That one is our demo model, so it doesn't matter if you drop it or bounce it around. But we have that, we take it along to like customer briefings and whatnot, so people get an idea of the size and the weight of what a laser terminal looks like. And I've got a picture of some earlier models, not ours, but from maybe sort of 20 years ago, and they were very different in terms of size and scale, etc. So what I wanted to talk about tonight was probably 2 main topics. So one is the design of the laser terminal. So why do we build it? How do we build it? What is it supposed to do? And also talk about a next generation version that we want to do. That one's for what we call terrestrial deployment. So if you're a telco like Telstra, you can buy those sorts of terminals. You need 2, one on either end, so they can communicate. And you can do all sorts of interesting comms type things. But we're also using very similar technology to do something from space. So we're building an optical ground station, and we're deploying similar tech into a satellite, so you can do laser from ground up to satellite, and then satellite to satellite, and then satellite back down to ground. So the idea behind that is that we can have a constellation of satellites, and we can deliver very high-speed internet pretty much anywhere that we want to do it. So we'll go through the design of this one first, and I suppose the first question is, why do we want to do it? And if you look at internet today, if you're a telco, as I mentioned, like a Telstra and Optus, etc., one of the things that's core to your business is you want to build a network that's got as much coverage as possible and that is as reliable as possible. And companies like NBN will do fibre to the node, so they'll use optical fibre. They'll get it close to where we live, etc. And then they have a problem they call last mile connectivity, which is how do you get from that node to where somebody actually wants to use the data? And sometimes getting there is really easy. It's like lay a fibre optic cable and you can run it down the street, you can connect in, and hey presto, off you go. Sometimes that can be really, really hard to do because you have buildings and concrete and roads and all sorts of things in the way, and trying to put a cable in is actually pretty hard. Sometimes it's very remote, ultimately too. So typically telcos like to have a range of technology options for how do they solve that last mile problem. And so where that device is focused is in helping that particular problem. The other thing that we find is that if you look at the whole population of the world today, there's around, 7+ billion people. There's around 3 billion people, just short of half, have no internet connectivity at all. So they're missing out, and a lot of those are in poorer countries and third world countries. So we take it as almost a right that we have a phone, we have internet connectivity, but there's a fair percentage of people that don't. And a lot of times in those countries, they actually don't live very far away from where an internet node actually is, but they haven't got connectivity deployed because it's too hard, too expensive, too difficult, etc. So we try and solve that problem with that device where we can do it cheaply and we can do relatively fast deployments. And the main competition that we have actually comes from radio. So if you're a telco today and you've got that problem where you can't lay cables, etc., you'll go and reach for radio, and you'll go and use microwave, some sort of radio frequency to solve that problem. And we have benefits and disadvantages and advantages depending on what the actual problem is that they're trying to solve. So if we're going to go build a laser terminal, there's a whole bunch of design considerations that goes into it. And we commercially have to be able to compete with the radio products. So we have to be within a certain price range to be able to do that. And so when it comes to the design of the terminal and how we manufacture it, there's a lot of engineering that goes into getting the price point right, the physical size, etc., correct as well. So one of the first things that we have to figure out and work on is for a laser-based device, what's the wavelength that we actually want to use to be able to do the transmission on. And I've got a slide I want to talk through. And this is a slide that was, I'm going to preface this. This was a slide that was put together by one of our engineers. And this is the electromagnetic spectrum, which I'm pretty sure some of you guys would probably be familiar with after all the radio work that you've been doing. And from the left, we have really long wavelength stuff, and over to the right.
Stand one side.
Oh, yep, I can stand a bit over this way.
Oh, even behind if you like.
Okay.
Yeah. Clear view of the screen, thanks.
And then over to the right, we've got really short wavelength. And radio and TV sits in slightly towards the middle there in terms of the sort of wavelengths that you guys will be using, I'm assuming, for the sort of radio work that you do. And depending where you are in this spectrum, there's different characteristics that are good or bad depending on what you want to do. So if it's the really long wavelength stuff out to the left, one of the things that you can do with that is you can penetrate things like rock. And if you wanted to, for example, be somebody who wanted to find caves and things underneath the ground, if you're into mining, they run devices with really long wavelengths that can actually penetrate ground, reflect back, and they can determine if there's openings, etc., under the ground. For us, what's interesting in terms of trying to send data over a laser is that the shorter the wavelength there is, the higher the bandwidth of the signal. And the higher the bandwidth because you have more waves going through. And the way that we send the data is that we modulate the wave. So for us, being at this end of the spectrum, for example, will give us fantastic data rates, but then it introduces some other problems. So this is quite dangerous to humans on this end of the spectrum. So we don't want to go and deploy stuff and kill people while we're doing it. And the other thing that we try and solve from a design point of view is I mentioned the cost of the device. And where companies that have done lasers previously have kind of fallen down a little bit is if you build a lot of custom components to try and make it work, then it costs you a lot more. And when it costs you a lot more, you start to price yourself out from a commercial point of view. So in going through and designing this, we kind of have to figure out where do we want to be in a spectrum that's going to give us really good data rates, and where can we be that we can get off-the-shelf components that are already manufactured that we can integrate and put into the device so we can keep the cost, etc., down low. The other thing that we have to kind of work through is that the more power that we need, so what distance, for example, that we want to transmit, we need more power to transmit longer distances. And the more power we need, the bigger and heavier the device becomes as well. So the other design consideration for us is, what do we think is the commercial distance that we need to do for the kind of market that we want to address? So we have to balance all those things out, and then the magic answer that we come up with is 1,550 nanometers is the magic wavelength that we use. And that sits here. And if you were Superman and you had heat vision, you'd be sitting here in a spectrum. And if you were the Death Star in Star Wars, you'd be sitting here in a spectrum. So our answer is somewhere in the middle between those two things. And at that wavelength, the fibre optic cable world, they have components that can deal with items in that wavelength. So it means that we can take mass-produced, cheap components to be able to do some of the processing that we need to do from a light perspective. The other thing in terms of power is 3 kilometres is the magic number that we do distance-wise. So we can do, in theory, at that wavelength, we can do terabits per second of data and bandwidth. We currently don't do that today. We do a 10 gigabit version and a 25 gig version. And what does that mean in terms of, I suppose, internet speeds? A really good speed at the moment that you would get from, say, Telstra or Optus would be 100 megabits into the home, would be considered a good speed. So 25 gig is like way in excess of that. So 1550 nanometers is a good wavelength for us. And, excuse me, in addition, excuse me, get my throat going. In addition to that, we look at the, I suppose, the price point, and we can, at that wavelength, get around about the same price as what a microwave link would cost as well. So that means when we go in and have a conversation with a customer, we can say, you can buy this for this price, you can buy it from us for the same price, but here's the other benefits that you get. The other thing that happens that towards this end of the spectrum is, I spoke about sort of penetrating through ground. At this end of the spectrum, you can't really penetrate very much. So even to the point of, if it's cloud, fog, for example, if you're in the radio sort of range and the microwave range, you can penetrate through cloud and fog. If you're here where we are, which is close to the visible light range, you can't penetrate cloud and fog. So what that means is that when we go to talk to customers, we can give much higher and better bandwidth, say, than a microwave link. But if it's a really bad weather site, so if you want to go to Antarctica and it's snowing for 6 months of the year, then you won't get a signal, ultimately. So for us, from a customer and sales point of view, there are certain problems that we can solve really well and other problems that we don't solve really well. Okay? So the other sort of smarts in this is that you can get rain, which comes in, and rain will reduce the signal that comes through. So what we've done to counteract a lot of the atmospheric conditions that can happen is we have automatic amplification of the signal. So if there's rain that comes into play and the signal starts to drop, then we automatically amplify that signal to compensate for the rain. So even though at this end of the spectrum we start to get affected by atmospheric and weather conditions, we can compensate for some of that. The other thing that happens for us is heat. So in Australia, for example, if it's the middle of summer and you're out in the desert, you see that mirage type effect that comes in and it starts to shimmer and move. So that creates problems for laser signals because the laser signal starts to move around. So one of the things that we've had to solve, and I'll go through some of the detail on it, is how do we adjust for all those atmospheric conditions and still get a really good signal? Because when you go into a telco, typically what they're looking for is what they call 5 nines reliability. So 99.999% of the time, you have to be up and working irrespective. So that's where we sit in the electromagnetic spectrum. This is what a laser terminal used to look like. So you can't fit that in your shopping bag. So some would say he's maybe overcompensating for something, but one of the things that we come up against talking to customers is they've already tried laser technology like 20 years ago, and that was what it was like. And this is using custom components, going for very high power for longer distance, etc. And it becomes very, very difficult to deploy and manage all that stuff and very expensive to do it. So commercially, we've had to look very closely at what we build and why we build it. But that's just an example of how it used to get done. And in terms of how the terminal gets deployed, often that would be on a telecommunications tower. So typically the way that happens is they have riggers, people who are trained to be able to climb up those towers and be able to do installations, etc. With the device that we've got, you can put that into a backpack and they can actually climb up with their harness, etc. and they can install that. With that, you need a crane. You've actually got to go to get that thing up there. Like a person can't lift it by themselves. So we are a long way forward from where things used to be. So how do we do it? So this is a walk through the processing that happens on the terminal. And on the left-hand side, there's a fibre optic cable. So this is the same sort of cable that would run into your house, for example. It's a fibre optic cable that goes into a thing called an SFP, which converts the optical signal into an electrical signal. And that SFP is a common component that's used by lots and lots of other fibre optic companies and cables. So that's one of the things that in picking our wavelength, we can use a really cheap component to be able to do that. So that's off the shelf. And then goes into a PCB, which is some electronics that we've designed. And it changes the signal. The signal that comes in from a telco could be a range of different wavelengths, and it could be a range of different power, etc. as well. So we take a range of input in, feed it into the PCB, and that PCB then morphs that signal into the wavelength that we like, the 1550 nanometers, and it morphs the amplitude of the light wave into an amplitude that we like, and it morphs the power into the right power rating that we like, so that we can then prepare to transmit that through the atmosphere. And out of the PCB, we get an electrical signal that goes back into another SFP, which converts that electrical signal back into an optical signal. And again, that's the common component that's fairly cheap for us to get. And then the next step in the chain is it goes through this thing called an EDFA, which is the amplifier component. So the amplifier is adjusted up or down depending on what's the atmospheric conditions that we've got that we need to try and work through. So in heavy rain, it'll amplify the signal, and it can amplify up about 200 times. From the EDFA, it goes into what's called a collimator, and that's a component that basically sends the signal out into free space. So that's the laser component. That's the thing that takes the optical signal and says, convert this into a laser that we're pointing, and off we go. And then on the other end, so that's going, it's transmitting out, we can loop around, and on the other end it's got to receive the signal. And that goes through a lens. So you'll see in the the device that got passed around, there's one big sort of lens and turret there in the middle. That's the main one for receiving the data signal. And that gets condensed down into a fibre. There's a receiver there that we've got for that converts it back into a signal on the fibre. And that kind of goes through the reverse path, which is it goes into an SFP, which converts that optical signal back into electrics, goes back through our PCB, which then converts it back into the signal that they're looking for going out the other side. So that's the cycle that we run through in terms of the data path. And in terms of some of the precision that's required for that, so the distance from the physical distance between the two terminals from here to here can be up to 3 kilometres. And that means that at 3 kilometres you've got to land that signal and get it back into a cable which is 50 microns or 50 millionths of a metre wide. So essentially from a 3 kilometre thing, you've got to land it on a dot that's 50 microns wide. And you've got to do that 99.999% of the time through scintillation, rain, and all sorts of things that might want to interfere with the signal. And I've got a slide I'll show you in a few minutes around how we do that part of it, or how we manage that part of it. So, any questions? Go for it.
So you could take a 1350 nanometer signal and convert it to what you want?
Yep.
1350 is pretty common in the local network,
Yeah, absolutely.
Right. Would you ever use diversity?
So we do. And we use diversity probably in a few different ways. So in terms of availability, the classic is we lose signal. So something blocks the signal here. And that could be like it's really, really heavy rain or cloud, for example. So often, our customers still want a signal. They still want to get the message through. So we can use diversity of tech. So we can fall back to a radio signal, but it's much lower bandwidth. So we have to drop some data to be able to do that. Or you have an alternate path. So you have multiple paths that you can use to get something through. So that's the data path. So that's part of what's happening inside that terminal that we passed around. The next thing is, and this is kind of where I think we've solved some problems that I'd argue are solved better than how they've been solved before for sort of previous incarnations of laser comms. The trick with any sort of laser comms is there's, in terms of the signal and getting it established between the two terminals, there's a thing called pointing. So you have to get the terminal pointing in around about the right direction of where it should be. Then there's acquisition. So you have to acquire the signal. So one is, am I pointing approximately in the right place? And then, can I acquire the signal? Can I actually see the signal coming through? And once I've acquired it and I've got it, I've got to track it because it can move and change, etc., with rain, scintillation, all that kind of stuff going on. So this is one of the core pieces of how this stuff works and is reliable. And the way this works is, from a pointing point of view, we actually go out and do what we call a site survey before we deploy anything. And the site survey is to go out and look at where they want to mount the devices. And we check line of sight. And we check line of sight to look for things that might interfere with or obstruct the signal. So an example of that might be there's this black roof that's sitting 2 feet below the signal going through, which means that in the middle of summer when that black thing is really, really hot, there's all this heat coming off and it's starting to cause scintillation and that kind of thing. We also look at the tower or the mount point. Is it going to sway and vibrate, etc., if it's windy or rainy and that kind of thing? But we go through and we do a site survey, and then part of what we get out of there is we get a camera view, like a picture of the other side from both sides, and we mark where that is. And then when the person who's doing the installation comes in, they get a view through the device where they can do an alignment to get that approximately right. So that is, they can line it up with as it was from the photo. Once they've got that, they turn the devices on, and the device then goes through its acquisition. And the way we do that is we have a second laser. So there's one laser which is the main one for doing all the data transfer at very high speed, and then we have what's called a beacon, a second laser. And the beacon is like a lighthouse. It's this thing that's sort of bright and has a very widely dispersed beam, so that for the device on this side, it's pointed approximately right, and it goes, I can see the beacon. The beacon is this bright laser thing that's coming back here, I can see. And the beacon communicates, so it has a signal, very simple signal that it sends through, and it can tell the device exactly where to get to for acquiring the data laser. So we have a data plane, and we have a control plane for controlling that as well. So in that device that passed around, there's actually 2 lasers, and there's 2 cameras for receiving signals. So that beacon also plays a major role in the tracking side of things. So in terms of the initial acquisition, it then looks at and interprets how is the laser signal going over time. So if the laser signal starts to drop, it can say to the side, you need to power up. Like it could be that there's rain coming through. If it starts to drop, it can also tell it to move left, right, up and down to try and maximise the signal that's coming through. And that all happens in real time in the space of sort of 1 or 2 milliseconds. So that is constantly looking at the signal and making adjustments, etc. So this path through here is really talking about how does that system actually work. And I'll start from this beacon driver here, which is our PCB for controlling the beacon. And then it has connected through to the beacon laser and collimator. So that's the thing that's looking like the lighthouse. And it's shining to the device on the other side, which has the camera receiver lens. And then it has a camera sensor. So we actually do image processing on what's been captured through. And that image processing is in the bottom half there, where we actually, believe it or not, have a Raspberry Pi processor that's in the device. And that does a few things for us, but one of the things that it does is it does some of the processing on the image processing. And so we've got some, and this is kind of where the sort of secret sauce and IP comes in, but we have some fairly good algorithms for interpreting that signal coming in to determine are we still accurately pointed or not accurately pointed. And if we're not accurately pointed, we generate this thing called a correction vector or error vector, saying you need to move in whatever direction to make sure that the signal is maximised. And then we have a microprocessor with some further control algorithms that controls a gimbal, which is the thing that's actually pointing the data laser. And that cycle there happens in 1 to 2 milliseconds. So milliseconds is about 1,000th of a second. So this is the thing that we feel differentiates us from a lot of what's happened previously. So I'll pause there if there's any questions or queries.
Is this tracking happening in both ends simultaneously?
Yep, both ends.
Looking for each other.
Yeah, correct.
And that's all in that box that you
Yep,
passed
that's
around.
all in that box. Not the big one that we saw before, but the little box.
So the small laser is the collimating one, is it?
Yep.
So the main lens is transmit and receive through that?
No, the main lens, the big one that you see, that's the receiver for the data. And
So what's the transmit laser like?
I can show you if we've got the device there. Can I pinch that and I'll...
Yeah, there's a bunch of optics in there.
There is a bunch of optics in there. So you'll see this is the main lens for receiving the data. Just above that, towards the back, I'll pass it around again, is the laser, the kilometre for sending out. And then to the right of it, on this side, you'll see a camera, a much smaller camera than this one, or the lens that's receiving the beacon signal. And just above that is the beacon that does the transmit out. So you'll see the four that are there. I'll have a look through that. So this is an actual deployment, and it's a good one because it's got a good story behind it that we kind of like, because it shows the advantages of the technology and some of the real world sort of use case of how people use it. And this is a deployment in Malaysia on the island of Penang. And what was kind of interesting is that they had no internet connectivity to the island at all. And this is Telecom Malaysia, and they have been trying to solve it for some time because the options that were open to them were run a submarine cable, which was incredibly expensive and not economic for them to do for the subscriber base that they had there. The alternative was to use RF technology, and they ran a trial on that, and they had a particular problem, which is from the mainland across to the island, obviously there's water in between. And what they found with the radio technology they had was that the main beam would go through, but it dispersed, and it would bounce off the water and come back up and interfere with the main signal. So it didn't work well for them. They didn't actually get very good reliability and not telco grade reliability out of it. And the other alternative is they go and give everybody a satellite dish and get them connected to a satellite. But that was also expensive for them to go and do. So they were sitting on it. They hadn't actually really sold what they wanted to do. And we sort of stumbled across this and said, look, we're happy to go put a trial in. We'll show you how this works. It works really well across, water and that kind of distance. And this is the installation. And it worked so well that people on the island got internet. They could get internet TV and that kind of thing. And it was just prior to the World Cup. And for the first time, they could see the World Cup live. And we phoned up Telecom Malaysia and said, we want to do some maintenance on the link. And we want to bring it down at 1 or 2 o'clock in the morning. And they said, no frickin' way, because that's when the World Cup matches are on. And everybody is watching it. So it was a good demonstration of how, there are particular problems in this last mile connectivity I was talking about that need to get solved, and telcos need options for how they solve some of the time.
So you didn't have problems with multipath off the water?
No.
Great.
So we have a very narrow beam that we go through, so it wasn't an issue at all. Okay, so that's kind of the ground-based stuff. And actually, one thing I didn't mention, I think, was that was one use case. Another, probably the main use case we have, is with mobile backhaul. 5G is kind of rolling out now. I don't know if you know, but 5G requires 10 times the density of 4G. So that means that where there's one 4G tower today, you need another 9 towers to get the coverage and density with 5G. And
so is that more antennas on the same tower, or
no,
spaced out?
Spaced out. So for telcos, that's actually like a very significant problem for a bunch of different reasons. So one is it's freaking expensive for them to go and do and deploy and roll out. So they don't want to do it unless they kind of have to. So some are cheating a bit, and they're doing what I call 5G Lite, which is they stick with their 4G tower and they put a 5G signal on it, and they go, okay, we're doing 5G. So you'll see 5G come up on your phone, but it's not really 5G at the end of the day. But to do it properly, they actually need another 9 towers. And to get that deployed, guess what? Most of it happens in highly densely populated areas that people live in, and there's office buildings and all sorts of things. And to optimise signal, they have to get the tower put in exactly the right place. So we're a really good option for that, because it means that they have to get the signal from the tower back into their main trunk. And we can say, wherever you've got your one tower now, which already has a thing back to the main trunk, you can deploy one of our laser terminals on that, and you can deploy another laser terminal on the new tower that you've got to put on. And hey presto, you've got very high bandwidth back to your backhaul. So we find a pretty good use case for what we call mobile backhaul as well. So space. Because we're, I suppose, a bunch of engineers, everyone sits around with nothing better to do, and we have people who know how to go and do space in the company. So it actually might be worth just spending a moment on that. I'm a software person. I know very little about optics except what I've been taught since I've been working at the company. But the engineering team, there are guys who are world experts in optics who know and have solved this problem of, okay, so what wavelength do we use and why, and what components do we need, etc. There are guys who are electronics experts in terms of designing the circuitry and PCB. There are guys who are mechatronic experts, so in terms of the gimbaling, that control loop of how we control the laser, etc. Experts in that. We've got experts in software, and no one's an expert in all the other domains. So it means that as an engineering team, everyone's actually got to work in a very cross-functional way to be able to get the device working. So it may mean that if we're having a problem on the software side, we can solve that in hardware. And the hardware guys can go, oh, actually, we can do that really simply or really easily. Or it might be vice versa. They're trying to solve something in the hardware that's really hard, but we can do software-wise quite simply, ultimately as well. But part of the, I suppose, original vision for the company when they were starting up was to have communication from space. And the idea behind that is that, I think as I mentioned before, you can have laser comms from an optical ground station up to a satellite, and then you have a constellation of satellites around the planet that then you can take that signal and go from satellite to satellite and then put that down into another optical ground station wherever it needs to get to. So if you're a mining company out in the middle of Australia in the boondocks where you got nothing, then you can get some very high bandwidth, high speed comms in for not a lot of money to be able to do it. So the device that we've got is the one that kind of helps pay the bills. That's what we market, sell, people buy. Space is purely a research project for us at this stage, and it's probably 2 or 3 years or more away from any sort of commercialisation. So we have to go through and develop and prove that it's possible. And that's what we're in the process of doing at the moment. And there's kind of 3 phases to what we're doing. And the first phase is, I spoke about, we've got 2 lasers in the device. So one's the control plane, and the other is the data transfer laser. The first phase that we want to do is just get the control plane going. So that is put the beacon into a satellite and be able to see that beacon and be able to communicate with it. So we can do like the PAT, the acquiring side of what's going on, and make sure that works before we do the data side. And the second phase is to then get the data layer going from ground up to satellite, and then satellite to satellite. And then the third phase is we want to be able to get that going in multiple paths. So that is, we have multiple ground stations, we have multiple satellites up there that we can actually do. And the first phase, it might be worth taking a step back and just maybe talking about what's changing in space and space economics at the moment. Because if we go back to, 60s, 70s, 80s, probably 90s and 2000s maybe as well, if you want to put something in space, it's incredibly expensive to go and do. And if you put something into space, because it's incredibly expensive to go and do, it has to work. So the traditional way of doing space projects was that they took years, took a very long time, they cost billions of dollars to go and do. And when they went there, the satellite would be there for like 20, 30 years. And that was the only way to kind of get an economic payback. And so the technology that was used was typically very old, because it had to be very reliable and make sure that it worked. So they were a bit averse to using new tech, and that was the way that the projects were run. The economics of how to get something into space have completely changed. And there's a new standard out that NASA have done called a CubeSat standard. And a CubeSat is a cube about 10 centimetres by 10 centimetres. And the idea is that you have standard componentry. So you have a satellite that might take a 6 CubeSat payload, for example. And if you want to have a payload go onto a satellite, you conform to that standard. And there's electrical signals and other kind of things that go into it as well. But the idea is that you build your payload to fit into that standard, and then you can go ship onto the next satellite that's going up. And you then have companies that specialise in just building satellites, and that's all they do as CubeSats, and they get very efficient and economic at doing it. And you get companies like SpaceX who get very specialised into doing launches, and they can do launches very cheaply and easily, ultimately too. And it means that the way you go about doing a space project changes completely with the economics. So rather than taking years and years and years and spending billions to go and get something up into space, you can get something really, really small that's actually quite cheap, and it doesn't cost you much to put it into a payload because it's one of a bunch of other things going up. And you do that with a rocket that's actually pretty cheap to get up as well. So what people are doing now is there's a lot of experimentation going on with what does that enable. So what types of applications can you do? What is it that you can do from space that would benefit things from the ground? So examples of that would be bushfire detection. So one of the ideas being mooted around was in Australia, bushfires every year, and not just us, but California and elsewhere, costs hundreds of millions of dollars and more in terms of damage. So the kind of envelope that people are pushing is you can from space see if there's heat, fire, etc., actually starting up. So let's say there's a lightning strike. So you could detect that from a satellite relatively quickly when that's happened. And if you can detect that, you can obviously pinpoint exactly where on the planet it is. So you can then raise an alarm, an alert, etc., saying this is here. You could take that a step further, and you could go and get drones to go out there and actually extinguish that thing before it becomes, too big or too large, ultimately too. So that type of thing is in play at the moment. There's people actually solving that problem and kind of have solved that problem with satellites. But the economics of it have changed very fundamentally. And so what you see with things like Starlink, for example, is they want to go in a similar way put up the constellation of very small satellites in very low Earth orbit to go and do internet connectivity ultimately as well. The difference with them versus us is they use radio, we use lasers, so we're much higher bandwidth. But so what that means for us here is in phase 1, we've already pushed our first satellite up, and we were one of 6 payloads, so we were one of those little cubes in a CubeSat going up, and it was launched. The rocket was launched by the India Space Research Organisation, ISRO. They have a launch base near Chennai in India, and the US company we work with, Antares, did the satellite, and for everybody, it was a research project. So for the ISRO, I think it was their 3rd launch with that type of rocket, and I think at least one of the previous 2 had failed, and they are trying to prove that they have a viable and reliable launch capability for small, medium and large payloads. And for Antares, they're trying to prove that they have a commercially viable model with the CubeSat model. And you would have heard of cloud computing and Amazon Web Services and that kind of stuff. So they have their control plane, if you like, for the satellite running on Amazon. So it means that for us as a payload, if we want to go and communicate with our payload on the satellite, we can do that using regular software and comms type stuff from an Amazon cloud service, which will get routed up to the satellite to switch our payload on or off and do all sorts of things with it. So they were proving that model. And then for us, we would like to prove that our beacon actually works, from space down to an optical ground station. And unfortunately, the satellite didn't work. So the launch was completely successful, and the deployment of the satellite was completely successful. But then the Antares side, they were using RF comms from the ground to the satellite to be able to switch payloads off and on. They couldn't get the RF comms working. So, and fortunately, they couldn't ever get it working. So now we're doing another launch in January of next year, and we're hoping that one will actually be a little bit more successful than the previous one. But there was probably any one of 1,000 different things that could potentially go wrong. And I was actually at a space conference in Canberra, the Space Industry Association of Australia, and I was talking about it there, and there's a whole bunch of people who had the same experience. That part of now the economic model has changed, is that you can actually launch quite cheaply. Like it was less than $100,000 for us to put that into space, and lots of people had a similar experience. So the model is more moving to a fail-fast model, where you try something, if it didn't work, then you throw another satellite up there and off you go again. So that is phase one. Now, the other interesting thing about our phase one project, so we design the hardware, so we design the laser, etc., that has to go up in the satellite. It has to go through vacuum testing, vibration testing, etc., so that it will survive launch, and that will actually survive in space ultimately as well. But it needs a ground station to communicate to. So something has to actually receive the signal and actually send a beacon back up to the spacecraft as well. And for that, we were relying on the Singapore government. So we partnered with the Singapore government, and we still partner with them actually for the phase two project that we're doing. But the Singapore government was going to do the ground station. And lo and behold, the government project ran late. And so,
Even in Singapore.
and so it meant that the ground station wasn't going to be anywhere near ready in time for when we were going to be launching. And so we had to do our own ground station. And for us, we built this thing we called TMOGS, which is just an acronym for Transcelestial Mobile Optical Ground Station. But we got a telescope, and it's a 24 centimetre telescope, which has is motorised. So it's normally used for like tracking a star as the Earth is rotating, etc. And we got some PhD students in from one of the universities in Singapore, and they reverse engineered the software for controlling the telescope. And we were able to get that to point and then track the satellite instead of actually tracking a star, and then receive the signal from the satellite and actually see what was happening. Now, unfortunately, we didn't get to test that bit because it didn't quite work, but yeah.
Okay. These are geostationary satellites you're talking about, low altitude?
They're not. So they're not geostationary. So we only get a window during the orbit when it's passing over Singapore to be able to acquire, and that window lasts for about probably 30 minutes.
Okay.
And
also you said earlier that your distance is only 3 kilometers. I mean,
on the ground, we go into low Earth orbit at 450 kilometres.
Yeah, that's a little different in the power department.
It is a bit different in the power department, but not as much as you might think. So for the beacon, we are about 5 times more the power from satellite, from the space, for the beacon, as opposed to what we are on the ground. And in fact, I should probably talk through just some of the power stats for it as well. So I mentioned that, and this is like on the ground, we'll talk about space in a minute, but on the ground, if you wanted a laser to, say, start cutting the table and start doing physical damage, you'd need to have power around 6 watts in the laser to start doing that. It would be 6 watts and higher. And for us, for the laser that we use, for example, for the data side, we vary the amount of power that goes in there. So if it's heavy rain, it goes up. If it's good conditions, it goes down. But if it was the heaviest rain at a 3 kilometre distance, which is our maximum on the ground, then we do 600 milliwatts of power to the laser. So 600 milliwatts versus like 6 watts is what you need to be able to do any sort of damage. We're like an order of magnitude less than what you'd need. So we don't have a problem with the laser in terms of doing any physical damage that way. So you can put your hand in front of it and it's not going to matter, even at maximum power. What it does have a problem with, though, is eyes. So if you were to stare into the laser while it was at maximum power, you can go blind in the eye from the laser. So it means that when we deploy, there's a work health and safety thing we have to run through where it has to be marked on the ground, or if it's on a tower, marked on the tower that there's a hazard. The device itself has to have all the sort of hazard stickers and things all over it. And we also, because we track the beacon and the image processing, etc., that we do, if we detect movement that looks like a person, then we shut the laser down and switch it off. So that's kind of on the safety side. But from the on the space side, I think it's around about 5 times the 600 milliwatts is probably what we get to. I have to double check the power on that. But we don't have any people type problems or issues with anything coming from space ultimately, because no one's going to be up there in their spacesuit that close to it that they're going to have a look at it.
If you're looking up, if you're transmitting from the satellite down.
Yeah, no, the dangerous distance from the satellite would be like 100 metres, something like that. So it's sufficiently dropped in power by the time you get down here. It's not an issue.
This doesn't work if it's cloudy, or does it?
What's that?
This doesn't work if it's cloudy, or
Correct. It doesn't work
it
if...
works on a clear day.
Yeah, so... and there's positives and negatives to that. So one of the positives is that Australia is a really good place to have an optical ground station, particularly out west in Western Australia and that kind of stuff. And we're actually working with the ANU, the Australian National University. They're actually building an optical ground station in Canberra. So we're going through the technical details with them, but we'll probably use that ground station for some of the stuff that we're doing also. But the thing with getting blocked by cloud is it comes back to the diversity thing before. Basically, if you have a constellation of satellites and you can go satellite to satellite, then you need multiple ground stations. And if you're blocked from a weather point of view going down to one ground station, then you reroute off to a different one that you can get the signal down ultimately. And I mentioned the space conference I was at. One of the things that so our thinking, like where we were coming from, was very much a telecoms perspective. So that is, it gives you a route to put internet traffic somewhere else, onto the planet, remote, very high bandwidth, that kind of stuff. What we hadn't realised until recently is that with all the economics that's changing around space at the moment, there's an awful lot of projects going up into space that need to get a lot of data back down onto the ground. And at the moment, they largely, 99.9% of the time, rely on RF frequencies to do that. And so they're generating a lot of data with those projects, but it's taking a very long time to get the data down. So we're finding a lot of interest with some of the space companies of how quickly can we get through some of the research that we're doing to help with some of that bandwidth too.
How severe is the atmospheric sort of optical disturbance? I mean, we all see stars twinkling at night, and this must be subject to the same sort of phenomenon. Does that make this tricky?
It takes a fair bit of scintillation, like a lot, to actually really disturb the signal a lot. And the reason for that is the pointing, acquiring and tracking system that we've got does the compensation for that. So it would have to be really, really bad for it to happen. And typically that's a fairly adverse weather event. So it happens with a mixture of heat potentially and cold going through. So generally we're kind of okay with it, but there are cases where it will upset the signal.
Do you use encoding and error correction on the link?
We don't. That's a good question. So there's a communications, the oversized stack. Yeah. So we're a layer 1 device. So as a layer 1 device, what that means is all we do is send a stream of bits. That's all we do. We just send bits. We don't do any error correction or anything else. And in the oversized stack, there are layers above that receive the bits, and then they do the interpretation of was there an error and a problem, and then they signal back for a retransmit and that kind of thing. But yeah, we keep it very simple. Yep.
Okay. How are you going to handle the software? Because I know Iridium had something like 6 million lines of code, all the handoff and everything else.
Yeah, we have nowhere near that.
So how are you going to manage the complexity of the software parts?
So part of it is we use off-the-shelf software components where we can. So the device itself that we pass around actually runs Linux as an operating system, if that means anything to anybody. So we run Linux, and so it's a more embedded version of it. And then the software that we run on top, I mean, we have a few 100,000 lines of code. We don't have anywhere near millions of lines of code at all. If you're technically minded, there's embedded software that we do. So we have a few microcontrollers. So things like controlling the gimbals that are doing that every 1 to 2 milliseconds, that processing is offloaded to a microcontroller. And the embedded software that we use is all written in C++. The main software that we use on the device and stuff like for web services and backend is in a thing called Golang.
With respect to from ground up into space, you can plug the gear into a power plant, so to speak. But from space back to ground, power to weight ratio, everything's solar, battery. The hardware to generate the power will be bigger than the actual laser. So, and you've got to go the distance.
Correct.
Otherwise, the better optics or more sensitive receiving, or things have got to run at ultra low temperature for noise and all this kind of jive. So there's a lot of external things that determine how much juice you can get back to ground.
Correct. And one of the things I was saying before about like the space economics side of things, if we were to build a satellite which was just for this, with what we would need from a solar and power point of view, then that would be a very different economic equation. So the thing with doing it through the CubeSat approach is that you have shared infrastructure in the satellite for the different payloads. So the satellite provider provides the solar array, the solar panel. They provide the electrics, and there's a spec for that. And each payload then just needs to worry about its individual part. So we'll get power from the satellite, but we don't care where the power comes from. The satellite provider actually does that and makes that happen. But if we build a dedicated satellite for it, then then we've got to do all that and make all that happen.
It's a shared resource,
Yeah.
Okay.
So the system's point-to-point only, isn't it?
It is, yeah. Yeah, which for military applications is actually quite advantageous. So we work with the Singapore military, and we've had some conversations with the military here in Australia, because one of the things that they don't like as much about radio is eavesdropping. So if they're out in a battlefield, someone puts an antenna up, they can try and crack and break, what's actually going on. With a laser, it's a directed narrow beam, and you can't eavesdrop that beam. If you try and break into it, you break the beam and you've broken the link, and we stop transmitting and all that kind of stuff.
You know, it expands by the time it gets Earth from satellite. How much that laser beam would have expanded?
Yeah, so our beam divergence is 0.01 degrees. And so from, I can't remember the exact diameter of what the beam is when it hits the ground, but it's not particularly wide. I mean, the beacon is designed to be wide, to be seen. The data, though, is quite narrow. But I can't remember the exact diameter when it hits the ground.
That prevents people from intercepting it as well.
You know, I heard an interesting fact which I never knew. You know, Pine Gap is out in the middle of Australia. Does anybody know why Pine Gap is out in the middle of Australia? So, Pine Gap is out there because, and I can't remember which decade it was.
It's a long way from a rocket launch.
It's a long way from a rocket launch, but it's a long way from the sea because the early satellites that they put up, they had no encryption on the satellite signal back down to Earth. And they didn't want the Russian ships and everything else, fishing trawlers, eavesdropping on the signal coming in from satellites because not encrypted. So they put Pine Gap out in the middle of Australia so they had control of nothing could eavesdrop on anything coming in from the satellites. But yes.
Right. Any
One more question.
Yeah, I
That's me.
saw on TV an item about a crowd in South Australia, I think it's Radio Owners, who built their own launching pad and their own rockets, and they're putting up these little pods. They're below the level of the current Centauri space station, but they're up there long enough for them to do some transmitting and receiving.
Yeah, you have to get permission to launch, ultimately. So one of the things that happens with a launch is that there's a UN group that you have to apply to say that you actually want to do a launch up. If you don't apply for that, so if a launch happens that people aren't aware of, you look suspiciously like a missile going off. That attracts a lot of the wrong attention. Yeah. So yeah, it is getting really cheap to actually put satellites into space. I mean, the other side of that is you get a lot of pollution and rubbish and stuff that ends up there. And yeah, exactly. And so everybody except China and Russia, pretty much, and probably Korea if they get around to it, North Korea, have signed up to a convention to say that they'll use space properly and they apply for different orbits and that kind of thing. So they try and keep things as separate as possible. But you still get other countries that don't. And for stuff that's in low Earth orbit, if anything happens, generally that will come down and burn up, and it's pretty small satellites, so it doesn't cause too much interference. But the big issue is if satellites collide, and then you get lots of, small pieces that go off in all sorts of different directions, and that starts becoming a problem. So as an example, I think it was Starlink and NASA in the last 10 months have had to do 50,000 orbit adjustments to avoid collisions. So it is a genuine issue. Like they do have to make sure they're missing out.
Apparently there was commercial and probably a Chinese military satellite.
There was. And
Got a bit close,
yeah, so I know the company. I actually visited them this morning, strangely enough, and they were quite, relaxed about the whole thing. So they felt there was a bit of a media kind of, okay, well, but everything is tracked that way pretty closely, and they knew what was happening, the Chinese knew what was happening, and they were quite relaxed that it was all going to miss and not be an issue. But yeah. But there is a potential.
Launch that you said failed, and you paid $100,000 to get it up there. Did you get the satellite back?
No. The satellite, it just decayed in orbit and just burned
So
up.
the question is, do you get the R&D tax concession?
Yes.
For work in Singapore?
Yes.
Okay, so it didn't cost you 100,000.
No, it didn't cost us 100,000. We got some dollars
line
back.
on the profit and loss statement.
Engineers had a lot of fun building it. Yeah.
Did you take out insurance?
No, they don't give you insurance for that, unfortunately. It's not worth it.
To handle multiple ground stations in your satellite footprint. So if you had 3 or 4 or 6 customers or 20 customers,
How would you get the data to all of them? You obviously got a timeshare or something.
Yeah, so
On the satellite.
so we, I mean, we can, for unless it's kind of a military customer and they say we only want our data on this satellite, basically it's like any sort of internet connection. We can run lots of customer data over the same connection. But there was a question before about is it geostationary, and it's kind of not. So yeah. So that means we do have to acquire, and the idea behind having a constellation is we have lots of satellites. So we have to acquire, have the data sort of flying as and when we need to, and then we'll lose that signal for a while. We'll switch to another satellite, acquire, and then carry on again. Yeah. Yeah. Yes.
Any more questions for John?
Frontier, yeah.
No more questions?
Okay.
Well, John, thank you very much. I must say this is one of the best talks we've had in a while. And the thing that you did very well is keep it nice and simple. Now, there's lots of people who understand everything you said and ask very intelligent questions.
Yes.
But I think the rest of us who maybe not so experienced in this stuff really got a good understanding. And am I right in saying your company's just up the road? Where's it based?
It's based in Singapore.
It's Singapore.
Yeah.
Is
So
an office up here or not?
No.
It's in Singapore.
It's in Singapore, yeah. So we're probably going to open an office in Singapore soon.
Okay.
Because we are talking to, I mentioned, like ANU and a few other universities and space companies here. And so we want to try and get some grants and some funding to help with all that. But to do that, we need to be an Australian entity as well.
So thanks very much, John. Really
Thank you, and thanks for the invite.
I just have one more question for you. How many of you have managed to communicate through a satellite this week? I did. I had my first contact through the International Space Station repeater. There was a guy up the road, I heard him. Yes, he was up the road.
Digital or voice?
A voice repeater, yeah. It's up on 2 meters and down 70 cents. Yeah.
So I have a question for you guys. There's a solar cycle that runs every 11 years. And it peaks next year in 2025. And I was told that with the peak, it interferes with like radio transmissions, that kind of stuff as well. Do you see that happen?
Oh,
Is that?
Oh, absolutely.
Yeah. Yeah, because in theory, this year and next year, we're heading into a really bad cycle of that currently.
Well, we call the peak the good cycle.
It's good, that's good.
Yeah. Low power signals should travel right around the world very easily.
Okay.
And when we're in the trough of the cycle, it's very hard to do that.
So it's better when there's a peak, is it?
Yeah. The
I
peak
thought
of
it
the
was
cycle
worse.
is what we want.
Because you want the
Ionisation
HFC
up
the
there.
ionosphere to come down.
Yeah.
And I can tell you today, at about 3:30, 10 meters was wide open.
Yeah, it's been open lately,
Yeah. So we look for the peak to provide the blanket to bounce off.
Okay.
And everybody gets depressed in reverse.
We're depressed usually for 5 or 6 years.
Yeah.
It's long-term depression.
Okay. Very good.